So I want to talk about modeling a bit because storing data in JSON is different than storing data in tables. And I'm going to sort of compare and contrast the two. I'm going to assume most people watching are at least passingly familiar with relational databases, maybe not with NoSQL databases. But I want to start with a whiteboard exercise. I drew this myself. I know it looks so amazing. The artwork is incredible, but I actually did draw this myself. Let's look at modeling this. So we're building a new system. We're gathering requirements. We haven't even chosen a database yet or a technology we're going to build it on. We're just whiteboarding out the concepts and say, okay, here's what a customer is going to have to store. Now there are four things that I think I want to point out here. Four properties of this data and of all data, I'd say. There's a rich structure to this data. So we have the customer, and the customer has a name, Helen Mallory, a date of birth. Those are attributes. There could be sub-attributes. So sub-attributes might be first name and last name, right? So we could break it down into sub-attributes, but there are attributes there of the data. There are relationships here to other data. So if you look at the connections right up here, we're not going to store customers inside of other customers, right? We're going to connect one customer to another customer. Maybe it's a family account, or when you log into Netflix, you have to choose which user you're going to log into, but Helen is ultimately the one that is the owner of the account, pays the bill, that sort of thing. There's a value evolution. So as Helen makes more purchases, we're going to add more items to her purchases data there. And the last one is kind of a big one. This is kind of the area that I think there's the most difference in terms of data modeling, is structure evolution. So we may look at this and say, okay, well, for our customer data, we need to store a credit card number and an expiration date. Okay, fine. But then a requirement comes down to change that and say, okay, now we need to store multiple billing options for this customer. Okay, well, we can't really store that as part of Helen's data now. It has to be kind of a nested structure or a substructure or related structure to Helen. So we're evolving the structure of the data as we go. And again, if you're like me, and I know I am, this is kind of what went through your mind when you saw that data. This is how a schema would look in a relational context, a relational database, SQL Server, MySQL, Postgres, something like that. These are the kinds of structures, the tables I want to create to represent a customer. The customer has contacts, the customer has purchases, the customer has connections to other customers. When that evolution comes down, well, now we have a billing table. So we have to actually go and change the schema. We have to create a billing table. We have to set up a foreign key constraint from billing to customer. We have to move the data from customer over to billing, and we have to remove those columns from the customer table. So that's at least 4 operations to change the schema that we have to do to make this change of 2 requirements. Now, that's, doesn't seem like a lot, but keep in mind this is a very simple schema. We've got 5 total tables here. I'm guessing those of you who work with relational databases probably have schemas with a lot more than 5 tables, and a lot more complicated things can happen to the schema. And for a large enough data set, changing the schema might mean you have to take the database offline or into read-only mode or something like that. And again, we're back to the 2 a.m. on Saturday. So that is kind of one of the trade-offs you make when you say we're going to follow a rigid schema. Then making changes could have some adverse effects on our system. Now, I want you to think about modeling data in a JSON world, and this is kind of a high level. I'm going to take you through an example here. But we should start thinking about grouping the data into something like an aggregate root. So if you're familiar with domain-driven design, kind of the same concept here. In fact, Martin Fowler once said that instead of calling these document databases, we should call them aggregate-oriented databases, which I think is a way, way better name, much more descriptive and accurate, but never really caught on. I'm showing you a table here, but don't think of it like a table. Just think of it like a big collection, a big bucket of data. And then each record in our customer collection there looks like this. So we have some JSON. And notice that we don't have a separate billing table. We don't have a separate connections table, or again, not table, but bucket or collection. It's all built in to that customer. So we've grouped it all, we've aggregated it all into that customer document into one place. So instead of having, potentially 5 different tables and 5 different pieces of data, we've got them all combined into one piece of data in a JSON document. Now let's look how to kind of represent the different things about that. We're going to break that down step by step here. So we'll start with one row of data in the customer table, And that's on the left is the relational model, and the right's going to be the document model. Right here, the translation is pretty simple. We're just storing the same data in JSON format. Pretty much the same thing. On the left, there's a CBL 2015. That is a primary key. And over here, we're not calling that a primary key anymore. It's kind of a similar thing, but it's a document key. It's the key that corresponds to this document. So kind of the similar process, but not exactly. Now I want to bring in purchases. So in Relational Database, it's a separate table with multiple rows, one row for each purchase. And then you see this is a foreign key that links this purchase row to this customer. This is the primary key and this is the foreign key here, and they match. So in the Relational Database, we've got 2 tables and we've got 3 pieces of data. And then normally to bring those together into our application, we have to do a join operation, or well, there's always going to be a join operation, but might have to go through an ORM, for instance, an object relational mapper, to try to convert it from this flat data into the actual object we're going to use in our language, in our programming, our application. So I like to think of this as you're taking the data from, let's say, your .NET application, your Java application, whatever, and you're going to take it and you're going to feed it through a paper shredder, individual strips, and you're going to store those strips of data. So, oh, this strip has purchase on it, so I'll put that in the purchases thing. And this one says customer, so I'll put it in the customer thing. And then when I want to get that data back out, I got to find all those individual strips and then tape them back together, and then off we go into the application. As opposed to the document database over here on the right, the purchases data is stored in that same document. So this is not a separate piece of data. It's the same document. But notice it's an array there. It's an array of purchases. And there's no foreign key in the purchases because it's not foreign anymore. It's domestic data. Connections. So this is an important concept if you're doing like a many-to-many type of mapping. We're mapping one customer to another customer. In a relational database, we'd often create like a mapping table or a join table, whatever you want to call it, that has this compound key, which is these 2 columns here, that consist of 2 foreign keys. So we're saying we're connecting this customer to this customer. And again, this shouldn't be named. This should be, I got to update the slide. This should be information about the connection. So this should be like brother or father, something like that. Something about the relationship. In our document database, it's again, kind of a similar thing. We have this connections array. So not a separate document, not a separate table. It's an array inside that table, or sorry, inside that document. And then each one of those items in the connections has a ID that connects to another customer document. So we know from here our customer Jane Smith has a connection to another document called SKR007. And that should probably say like brother or something, but maybe her brother's name is Sam Smith. We just want to store that here for convenience sake. It doesn't matter. But a whole separate document with a key of SKR007 is out there that has its own date of birth, its own billing, its own connections, etc. So let's put it all together. Here are the 4 tables on the left, and this is the 1 document on the right. So we've got 7 pieces of data in 4 tables, as opposed to 1 piece of data in 1 document called CBL 2015. So you can see we've got, instead of all the different pieces that go through the shredder, they're all in one place there in the document. Now I've made the rookie mistake here of putting card number, expiration, and card type in the customer table. If I want to add multiple billing options, that's not going to work for me. So we're going to need to go ahead and create a billing table. And so I have to go through all the schema changes I mentioned earlier on. But now we have 9 pieces of data in 5 different tables that we have to join together. And the equivalent over there is the document on the right. Again, we've got, instead of having it at the root level, I've got this billing array that contains that data. Now, one thing I want to point out here, one key difference between these two, and this is something that may make you uncomfortable if you're used to relational data, or you're used to the schema being enforced by the database, is that this document here is CBL 2015. This one is CBL 2016. So, you know, they both say Jane Smith, but kind of ignore that. It should be Bob Jones here, shouldn't it? Yeah, it should be Bob Jones. But they're 2 different documents. They live in the same database, though. So this one has the card number at the root, and this one has the card number inside an array. Those both can live side by side. And this is the flexibility I'm talking about, that these documents aren't related to each other. They don't have to follow the same schema, the same map. At least the database isn't enforcing that. So there's different strategies for dealing with that. You don't want to just go Wild West and have every document look different out there. Of course not. But you may want to evolve your structure over time. With a document database, you don't have to shut down. You don't have to change a schema. You can just start storing different documents when you want to. And then what do you do with the old documents? Well, that's up to you. There's different strategies for how to deal with that. Or some might say more responsibility to deal with that. All right, so that is it. That is my sort of crash course to modeling. But it's important to understand that because we're going to get into what would we want SQL to look like for this data. We're aggregating it up into sort of larger documents, sort of root level documents, instead of splitting them out a bunch of different tables. Let's talk about the approaches that don't use SQL. Which NoSQL databases have more than one approach to read and write data out of them, more than one API. And you're going to use the one that best fits your use case. But the simplest one is KeyValue Approach. So we talked about the key earlier. If you know the key ahead of time, just ask the database, give me the document that corresponds to this key. The document returns, or the database returns a document, and away you go. Really, really quick, efficient, simple way to read and write data. And the only problem with this is that you have to know those keys. If you don't, you might want to, if you only have key value access, you're going to have to port your data to some other way in order to access it via key. And that's not going to be super convenient for some use cases. If you can do key access just for one piece of data at a time, this is always going to be the fastest way. The MapReduce I mentioned earlier, this is where you're going to write a couple of pure functions, and they're going to run against every piece of data ahead of time. And as data changes come in, they're going to have to rerun those functions, and they compute the results ahead of time. So they may be stale for some period of time, or maybe you can enforce, don't make this not stale, things like that. But think of this kind of like materialized view, if you're familiar with that concept. This is great for aggregations. And it's fine when you don't know the key to access the data. You can query it. Basically, you can look at a MapReduce and look by other attributes of the data. And it's really good performance. They can run in parallel. So they're pure functions. They can run completely in parallel, and away you go. It is somewhat limited though in what you can write in a MapReduce. Ad hoc is difficult to do because you have to run these functions ahead of time and see what their results are. Unions and joins are typically not possible. Now, we are aggregating our data more, so maybe we don't need unions and joins as much, but sometimes we still do. And again, back to my very first point of the slide deck, it doesn't feel as natural to me to query data like this as a SQL query does. And then I mentioned this, of course, at the beginning. Document databases have some other type of querying language or syntax available. This is a MongoDB example. This is a screenshot right from the documentation. These languages are somewhat limited compared to SQL, and many developers abstract these behind tools like Mongoose, for instance. Now, Mongo is always improving this language and adding new features, so trying to keep up with SQL and the things that developers expect to be able to do. But beyond the raw technical story, ultimately, I think, anyway, this is just an opinion, that using JavaScript or a JavaScript-like language like this, a sort of a imperative language, it doesn't really feel as natural or as powerful as a SQL does. And for many developers who have been using SQL their whole lives to interact with data, this is a tough transition. You got to learn a whole new language. And not only that, you have to convince the rest of your team to learn a whole new language as well. So it could be a tough transition, a tough sell. So I think SQL would be the answer for this. But what would that look like? Let's look at how SQL for JSON should work. And I'm going to use a model as an example here. This is some travel data. We're going to focus just on the airline and route. Ignore the airport and landmark for now. I want to find users. I want users to be able to find flights between given destinations. We used to be able to get on airplanes and travel around the country, travel around the world. I know, crazy, right? But I want to be able to find flights between given destinations on a specific day, sort of things like that. So this is actually a data set that ships with Couchbase. This is why I'm using this as an example. It has airlines, routes, airports and landmarks. We're just going to look at airlines and routes today. So let's zoom into a route document. There's lots of route documents, but here is one of them. So notice that it has a source airport, and a destination. So that's kind of the definition of a route. It goes from one airport to another. It also has this type field, which I've said is route. That's not a required field. It's not a magic field. It's not a reserved word or anything like that. It's just a convenient way to organize data. So it could just as well be underscore type or doc type or whatever you want to call it. Class, underscore class is what you see sometimes in the Java world. Also notice it has this airline ID field, which you can think of kind of like a foreign key. I've got it in quotes here though. It's not exactly a foreign key because it's not a constraint, but it is saying, well, if you want the airline, go look up that airline document to get that information. And then the schedule down here is an important thing I want to point out. So this is, in relational databases, this would typically be 3 rows in a different table. It'd be separate from this route, but it's been denormalized into a single document here. So we have the entire schedule for this route available in this route document. And speaking of this airline 24, let's go look at that document. So it's a separate document with a key of airline 24. This is relatively flat data, so no arrays in this one. But also notice it has the name here. So if I want to get that name, I could just go look up this document and pull the name from here. It also has this type field. It's a different value. So I've just chosen to use type as a convention here as a way to organize my data. I'll split it up by type. So let's look at how a SQL query to access this data might look. And the only part of this query that might look a little weird to you is line 4. A travel sample is not a table. So if you're in a NoSQL database, you don't have tables. Couchbase calls this a bucket. Cosmos would call this a collection, I believe. And there's other different names for it. It's the same kind of concept. It's a bunch of documents. It has route documents, but it also has airline, landmark, and airport. So on line 5, I'm saying, well, just give me the route documents. I only want the route documents. And then line 6 is just give me the first 10 of those documents. So what would you expect the outputs of this to look like? If you guess something like this, you were right. You're selecting just the airline ID, destination airport, and source airport. And that's what you're getting. You're getting back an array of the data that you selected. But notice now we don't really have enough to serve our users because we have this airline ID, airline 137. We can't show that to an end user. They don't know what airline 137 means. So we want to get the airline name. So to do that, we could do a join. And again, if you used SQL before, this should look relatively familiar. Line 6 and 7 is probably the weirdness there, a little bit different. We're joining a bucket to itself, which, joining a table to itself is not unheard of in SQL. But remember that our bucket contains all different types of documents. So this is actually very common. And then line 7, we're going to join the airline ID value. So it's what airline 137 equals, and that meta keyword there. And this could vary from database to database, but in Couchbase, this is how we say the document key in SQL. So we're just joining this document to a document key, or to another document based on its key. Again, kind of like the foreign key constraint, foreign key concept. And the end result of this would be what we had before, but now you can see from our query, line 4, we're selecting name. So there on the right, you'll see line 5, line 11, line 17. They all contain the airline name. So now we can show this to our customers and say, oh yes, there's a route going from MRS to TLV. I don't know what MRS is. TLV is probably Tel Aviv on Air France, assuming they're still in business. I don't know. This is old data. All right. So there we've done a simple join. We've got 9 lines there in SQL that can be read by just about anybody who's written SQL before, or even just read SQL before. And, as opposed to a MapReduce series of functions or some sort of other proprietary query language, we have to go through and figure it out and parse through it and do a whole thing. When we already know SQL, SQL is a great language. Let's just stick with it. Aggregation, this would be a very similar thing. So I want here to find all the airlines that have more than 2,000 routes. And again, this is old data. I don't know if there even exist that many routes anymore. But then I'm saying on, this is kind of where the title of this presentation comes from. You can see I'm select and I'm doing a count. So I'm an aggregate function to count the number of flights. On line 8, I'm having my count and greater than 2,000. and I'm going to order it by the highest first. So order by count descending. And there you go. You can see only 2 airlines have more than 2,000 routes, American and United. Again, this is old data. I don't know if that's really the case anymore. I'm surprised Southwest isn't on there, for instance. And I want to dig into something that's a little more specific to JSON and NoSQL databases. And this is the idea of unnest, which I would also call an intra-document join. So let's do another query here. I'm selecting the airline, the destination airport, and the schedule. If you remember, the schedule is an array. So that's what the results would look like. If I blew up that schedule, you'd see it was an array of objects that have day, flight, and time. This is my query, and one of my results, one of the fields I selected is an array. So this is a plain select. There's no join happening here, but one of the fields is an array. And that's fine. That may be fine. You may want to go with that. What I also might want to do is flatten that out. So line 7 here, I'm going to unnest the schedule into S here. I'm going to unnest it into. And this is kind of think of this like a cross join between a document and the array that it contains. Yeah, devs always skip a few steps. Yeah, we don't need to read the whole documentation. Let's just skip ahead a few sections. that's right, lucky number 7. So think of it like a cross join between the document itself and the array that it contains. So it's going to decompose that JSON hierarchy and kind of flatten it out. So here's how it would look if I do that unnest. You can see now that the results have kind of blown up here. There's going to be a lot more results because I'm unnesting them. I'm flattening out that array. Kind of would look better in a table view. Maybe we'll do that if we have time for a demo. There's also nest, which is kind of like the reverse of that. It's another type of inter-document join, but instead of decomposing it, it will encapsulate the JSON. This is also known as join in Cosmos. So if you're using Cosmos DB, they don't use the word unnest. They just use the word join. It can be a little confusing, but that's the direction they decided to take with it. So there's lots more examples we could go into of SQL against JSON, but I wanted to just do this quick comparison here that the SQL language operates on a set of relations, and oftentimes we think about relational and we think that means relationships. Oh, relational database, that's because I can have foreign keys and things like that. Well, no, that's not exactly what relation means. A table is a relation basically. And I'm being maybe pedantic here, but that's a key difference between relations and relationships. SQL language operates on a set of relations, which are tables, and then projects the results out to a result set, or a type of table basically. And then the result set needs to be mapped to something in the application. We mentioned earlier the ORMs. This could be complicated. It could be relatively simple. And then maybe at some point it even gets mapped into JSON, right? It's for an API endpoint. For our SQL for JSON, we have, instead of a bunch of little tables, we have sort of these bigger aggregate documents here on the left. And we run those through a SQL query. So Couchbase's version of SQL is called Nickel, N1QL. So if you're familiar with databases, like SQL Server has T-SQL, Transact SQL, Oracle has PL SQL, Couchbase has Nickel, N1QL. There's going to be fewer types of documents because of the aggregation and denormalization, but you still might want to do some joining. So you might want to join a customer to loyalty info or orders to the customer, things like that. And then you go through the joins here in Nickel and you get the result, which is going to be the JSON. It's going to be a complex, structured or semi-structured object in JSON. And so you can take that result and serialize it directly into your C# objects or your Java objects or whatever. And you don't necessarily need an ORM here because there's not a mismatch between the data being returned by this query and the data you're going to use in your application. Here's the Cosmos version. It's a similar sort of thing, but notice that the arrows between the different documents went away because as of right now with Cosmos, you cannot do joins between documents. So it supports the unnest, but does not support the inter-document join. Basically, they've said we're not going to support that. So that's what's going on with Cosmos. And just to give you kind of a bigger picture, I can't cover all the SQL syntax today, but I want to show you this bigger picture diagram. So think of this big blue blob here as kind of like an ANSI SQL standard. Now, which standard? Okay, well, we can. That's a question for another day. But maybe it's 92, maybe it's 2016, whatever. But all the stuff you'd expect SQL to do is that big blue blob there. This larger blue circle contains a bunch of extra stuff you need to work with JSON, to work with arrays and nested objects and missing fields, things like that. And that's what NCL is. You think of it like a superset of SQL, or SQL++, as I like to call it sometimes. And we're going to talk about the extra stuff here soon. And then just for completeness here, the Cosmos SQL API, it's kind of 1 foot in both worlds. So it's not going to cover the whole SQL standard, right? There's no insert, update, delete, merge, for instance. And we already discussed there's no join. But it does have extra stuff to deal with JSON, because there's still going to be nested arrays or nested objects and arrays in Cosmos SQL. Extra stuff for JSON. So we don't have to go into huge detail on this, but because there are arrays and nested objects, we need some additional features to deal with that. So I want to point out there, second to last row, nested traversal. So if we have a nested object and an object nested in that, we need to be able to address those. So we add dotted syntax, select x.y.z. That'll get you all the way to z. Or if we have an array, we want to select a specific item from the array. We say array, give me the first element of the array, a bracket 0 bracket. We can range over those collections too, the very first line there. So we don't have to pull out an individual array element. We can range over the whole array collection, for instance. And then missing. So earlier when I showed you that example where one document had billing array and one document had billing data at the root of JSON, if one document has fields that the other documents do not have, we can use the missing keyword here to search for those. So if document A has first name, last name, document B has first name, middle name, last name, we can find examples of both of them. We could say where middle name is missing or where middle name is not missing. And then we can make some decisions about, well, do we fill it in with data? Do we process it differently in our application? That sort of thing. That's one way you might want to deal with that. So lots of other stuff going on there, dynamic construction, filtering, unset, which is something that's kind of weird when you first learn about it. You know, you have update set x equals foo, where you can also unset and completely remove that field, which just doesn't make sense in a relational field. Now let's get to Molodec's question here. Questions about indexes. So indexes are just as important, if not more so, than relational. So I know I'm guilty of this when I would code with relational databases. If I'm just creating a smallish table, I'm not gonna beat myself up if I don't create an index for it. Oh, whoops, I forgot to create an index. Not a big deal. If I have to scan the whole table, it's a small table. It's not gonna hurt anything. But back to the NoSQL world, all of those documents are in one heterogeneous collection. So if I have to scan the whole bucket, the whole collection, that could be a huge amount of data. So we want to avoid scanning the entire collection, the entire bucket. And that requires careful indexing. Now, one of the things you can do if you want to just take a shortcut, you can say create primary index, and that allows you to scan the whole bucket. All right, we can create what's called a primary index, which is basically turning on table scan and saying, I don't care about performance. I just want to get the query working. Not recommended for production, but a useful development tool. Down there at the bottom, I have a more useful index. I'm just indexing the type field. You can see at the bottom, I'm creating an index named def type, and it's on the travel sample bucket, giving it type. Now, that's a very simple index. You can also add compound indexes or multiple fields so that you can have covering indexes, functional indexes, partial indexes, adaptive indexes, which are a little more efficient way of dealing with unknown queries or ad hoc queries. Then the primary index can be a lot more performant. So I'm not going to go into indexing here much more than this, other than to say indexes are crazy. Your question was about execution plan of SQL queries. There's probably no point in indexes. Well, as you're going to see here, it's absolutely important to think about indexes. So if I'm going to look at this query here on the left here, I can put an explain in front of it, and then I can get out the results on the right. And that is the query plan. And you can see which index it's using. And so if it's hitting an index you expect it to or not, that's going to be important to factor into your performance. So that's one way you can do it. And this is in Couchbase. I think the explain command might be in Cosmos. I'm not 100% sure about that. But it'll give you certainly different output. But then, of course, depending on which tooling you're using, you can also visualize that index. So this is a Couchbase planned visualization like you'd see in SQL Server or whatever other tool you're using that shows you all the different steps of the query and what's taking up the most time. Is it using the correct index? Right here, the fetch step seems to be the slowest. 37.9% of the query is on fetch, which makes sense. So maybe this query is as good as it's going to get. Or maybe we can skip the fetch. If we want to use a covering index instead, we can skip this fetch step, for instance, depending on what we want to do. But yeah, planned visualization there. So you can look at the raw text, you can look at the visualization, and make decisions about how to tune your queries. All right, we're coming up towards the end here. So I want to show you kind of a comparison here. We've got your standard relational SQL in the first column, or the middle column, and SQL for JSON. And this all the different features about them, how they're kind of similar and how they're kind of different. So obviously at the bottom there, we're working with tuples, working with relations in the SQL world. With NoSQL, working with JSON and sets of JSON, arrays of JSON. You have data types that are, in SQL you have lots of different data types. Although for me, I think just make everything varchar 5000. That's the easiest way to go, right? That's a little joke for you there. Hopefully you're not doing that, but yeah, you have varchar and int and small int and all those types of things. With JSON, you have the standard JSON data types, right? You have number, string, null, boolean, object, array, things like that. And then a quick comparison of NCL, which is Couchbase's language, and Cosmos's, which is Microsoft's Cosmos SQL language. And this has changed a little bit over the years. Cosmos has actually added in some things recently to put more yeses in their column. But you can't do an insert, update, delete, merge with Cosmos. You do those with other operations, with key-based operations. As I mentioned, you can do an intra document join in both. It's called unnest in SQL, and it's called join in Cosmos. You can't do an inter document join with Cosmos, but you can do that with SQL. With NCL, it's called join and nest. Aggregation is now there in both. Until recently, Cosmos didn't have that. And you can do sprocs, triggers, and UDFs, kind of in both. So they're called those things in Cosmos. In Couchbase, you have UDF, and you have something called events, which are not exactly like triggers, but you can respond to data that's changed or deleted with some JavaScript code that you write. A mix of JavaScript and SQL.